Θα μου επιτρέψετε να πω δύο λόγια για το βιογραφικό του σημείωμα, τονίζοντας πρώτα απ' όλα ότι είναι ένας φιλέλληνας. Είναι ένας άνθρωπος ο οποίος έχει ενισχύσει πολλές φορές με την παρουσία του το σχολείο των στοιχειωδών σωματιδίων στην Κέρκυρα και έχει βοηθήσει και πολλούς Έλληνες φοιτητές. Λοιπόν, ο François Englert γεννήθηκε το 1932 στο Βέλγιο, πέρασε πολύ δύσκολα παιδικά χρόνια λόγω της καταγωγής του, έχει εβραϊκή καταγωγή και διέφυγε οριακά το ολοκαύτωμα μετά την κατάληψη του Βελγίου από την ναζιστική Γερμανία κατά τη διάρκεια του Δεύτερου Παγκοσμίου Πολέμου. Ακολούθησε σπουδές ηλεκτρολόγου μηχανικού στο Ελεύθερο Πανεπιστήμιο των Βρυξελών, οι οποίες ολοκληρώθηκαν το 1955. Στη συνέχεια πήρε το διδακτορικό του στις Φυσικές Επιστήμες το 1959. Από το 1959 μέχρι το 1961 εργάστηκε στο Κορνέλ, στο Πανεπιστήμιο Κορνέλ και στη συνέχεια επέστρεψε στο Ελεύθερο Πανεπιστήμιο του Βελγίου, όπου έγινε καθηγητής και από το 1980 είναι επικεφαλής της ομάδας θεωρητικής φυσικής του Πανεπιστημίου. Το 1998 του απονεμήθηκε ο τίτλος του ομότιμου καθηγητή στο Ελεύθερο Πανεπιστήμιο των Βρυξελών. Έχει σημαντική ερευνητική συνεισφορά, όχι μόνο στο θέμα που προανέφερα, αλλά στη στατιστική φυσική, στην κβαντική θεωρία πεδίου, στην κοσμολογία, στη θεωρία χορδών και στην υπερβαρύτητα. Για την έρευνά του στη θεωρητική φυσική στοιχειωδών σωματιδίων που περιέχει όλα τα προηγούμενα, έχει τιμηθεί με πολλά σημαντικά βραβεία. Η κορονίδα όλων βέβαια ήταν το βραβείο Νομπέλ το 2013, το οποίο μοιράστηκε με τον Πίτερ Χίξ, όπως είπα προηγουμένως. Και όπως αναφέρει η αιτιολόγηση του βραβείου από τη Βασιλική Σουηδική Ακαδημία Επιστημών, του απονεμήθηκε το βραβείο για τη θεωρητική ανακάλυψη του μηχανισμού, ο οποίος συμβάλλει στην κατανόηση της προέλευσης της μάζας των υποατομικών σωματιδίων μέσω της πρόβλεψης ενός κατάλληλου νέου στοιχειώδου σωματιδίου. Μια πρόβλεψη που επιβεβαιώθηκε πολύ πρόσφατα, δηλαδή το 2012, δεν κάνω λάθος, από τα πειράματα Atlas και CMS στο μεγάλο επιταχυντή LHC στο CERN. Σας ευχαριστώ και ο προφέσορ
και ο Διευθυντής του τομέα φυσικής.
Θα είμαι πάρα πολύ σύντομος. Θα ήθελα να σας ευχαριστήσω όλους για τη συμμετοχή σας. Άλλωστε δεν ήθελατε να ακούσετε εμένα, ούτε τον Κοσμήτορα. Το μόνο που έχουμε να σας υποσχεθούμε εμείς είναι ότι θα κάνουμε τα δύνατα δυνατά στο πλαίσιο των εορταστικών εκδηλώσεων για τα 15 χρόνια της ΣΕΜΦΕ, να έχουμε και άλλους πολλούς διακεκριμένους ομιλητές μέχρι το τέλος του έτους. Και πιστεύω να απολαύσετε όλες αυτές τις παρουσιάσεις. Monsieur le professeur, merci beaucoup que vous avez décidé de visiter notre pays et donner cette présentation à nos étudiants. Bon, moi, je suis étonné de voir τόσους πολλούς.
So, we are very happy and honored you are here, and it's your turn now. Thank you very much for your presence in our school.
Well, first I want to hear if I'm heard. Yes. Well, thank you very much for these nice words. At least I suppose they were nice because I did not understand anything. But except, of course, what you see. And it's a great pleasure for me to be here and back, actually, to see old friends. And so this will be the subject, and the subject is related, well, to what you probably know or don't know, I don't know, but we'll see later if I can do something about it. So let me situate the problem. You see, there were impressive developments on physics in the first half of the 20th century, to the point, really, that one could even conceive, and some people thought even that like this, that all phenomena from the atomic scale to the edge of the visible universe could be ruled by two laws and two known laws, essentially. One was general relativity of Einstein, which is the generalization of the old Newtonian theory of gravity, and quantum electrodynamics, which is the quantum version of the Maxwell theory of electromagnetism, which is supposed to explain every electric magnetic phenomenon and all the propagation of electric waves, means essentially all kinds of lights. But you see, gravitational and electromagnetic interaction are what one calls long-range interaction, meaning that they are felt by objects no matter how far they're separated from each other. It's obvious from the light because you can see the star, and it's obvious also for gravity because they rule, in particular, the motion of the planets and even the galaxies and clusters of galaxies. But the discovery, actually, of subatomic structure below the level of atom, at the level of the nucleus of the atom, and below, as you will see, had revealed the existence of other fundamental forces that are short range. That means they're not really felt on larger distance scales than these subnuclear scales. And in the beginning of the 60s, there was no theory and no consistent theory interpretation, rather, of the short-range interactions. Robert Brout and I, and independently Peter Higgs, initiated a solution to this problem. Robert Brout passed away in 2011 and left me alone to tell this story that, as you will see, shed lights on the origin of mass of the elementary constituent of matter. Now, the first question, of course, which I'm going to treat is, why do we need a theory of mass? Of course, we need all the theory of things we don't understand, but why a theory of mass? There's a lot of things that we do not know, all the parameters and all the things like this. But why should we not say, well, mass is just something we don't know. We put in the experiment and we do something out of it. As you will see, it's not that simple once you try to make a theory. So the first question, why do we need a theory of mass? And that will lead us to a concept which played a big role in the understanding of this problem, which was spontaneous symmetry breaking and its generalization, which is the BEH mechanism, the Brout-Englert-Higgs mechanism, and its constituents, which are scalar bosons. And I will then discuss the discovery, or very rapidly evoke the discovery of the boson, which was essentially explained the theory, made the theory, verified it essentially, directly, and then I will show how this delineates the known from the unknown, both in the elementary particle range and also in cosmology, and the link between the two will appear clearly, I hope. So let me start. Why do we need a theory of mass? As I said, we have a theory already in the 60s. We knew general relativity, we knew electromagnetism, but there's a big difference between these two, because electromagnetism was valid not only classically, but quantum mechanically, and that's why it could be explaining things at the very small range also, despite the fact it's long-range forces. For instance, it explained all, essentially, the background of chemistry was explained as an effect, essentially, only of quantum electrodynamics. And so, that means Brout and myself, we thought that the theory of short range should be inspired from this, and should be essentially related to these long-range forces. So we decided to look into generalized theory. So first, electron dynamics, as I said, transmit long-range forces of electromagnetism. Why? Well, because this is a Feynman diagram. Times rubbed here from bottom to top. This is an expression of a scattering of two electrons. And despite the fact that this is a precise mathematical expression, this has, of course, a very intuitive thing. You see that the two electrons scatter because they exchange another particle, which is called a photon. Now, the photon is massless. And because it's massless, it goes with the velocity of light, which is the fastest velocity possible. And therefore, simplifying a little bit things, this is why this is long range, because the photon can travel a long distance. And the fact that it's zero is a consequence of local symmetry. So we decided that because this works, and it's the only theory that worked at that time, both classically and quantum mechanically, that is a generalization. We're going to introduce generalized photon. That was the theory which was known. It's a Yang-Mills field gauge theory. It's a theory which contains generalized photons, which can interact between themselves, can be charged, all things that photons cannot do. But they are massless as a consequence of something called the local symmetry, which I will explain. Then the question is, well, how do we get short interaction if we want to get inspired from this? The obvious answer, this is an expression in which a particle called the mu meson decays into two neutrinos, different neutrinos. One is actually an antineutrino to give rise to an electron, and which has a lower mass. So this with a W, this quantity there, which is massive, and which is a Yang-Mills field, or at least we hoped it would be at that time. Actually, it's not we, it's later, doesn't matter, but we thought about things like this and like others, but which were transmitted by Yang-Mills gauge field. So here the question is, if we want this to transfer short-range forces, an object like this, which is a generalized photon, which I just said is massless, we have to give it mass. Because if it has mass, then it propagates slowly, because it cannot reach the velocity of light. It propagates slowly, and therefore transmits things at shorter range, intuitively, right? It's a bit more complicated in detail, but this is like this. So how do we get vector boson masses? That would solve, perhaps, or would initiate the solution of short-range interactions. Well, the idea would be because there is this symmetry, which I will explain, which guarantees that the mass is zero, we have to break it. So this would lead us to break the symmetry spontaneously, which is a feature I will explain. Now, there's another thing, which also leads to the same idea. Massless fermions, you see, have a different symmetry than massive fermions. For instance, the muon here is an object which has a mass. But the neutrino has a very, very small mass, and in the beginning the theory was formulated in such a way that the mass was zero. So how can we have a theory where a gauge field interacts with a massless particle and a massive one? Actually, this is not possible in a simple way. So you would think that you have to put the muon to be massless, but that process would never exist then. So what can you do? Now, the electrons, the muon, the electrons are massive, and massless objects of that type can be viewed as composed on a superposition of two neutrinos. A neutrino says left and right. The left and right means that the spin, which gives the orientation of the way the thing propagates, is parallel or anti-parallel to its velocity or to its momentum. And this is possible for massless particle, but a particle which has a mass constantly travels from a left-hand neutrino to a right-hand neutrinos. But when you have two different neutrinos, which, like in a massless fermion, if you wish, particle has the property of not interacting between themselves, that means there is an arbitrary quantum phase between the left and the right hand. But that quantum phase is broken, so there is a symmetry, which is a rotational symmetry or a U1 symmetry in language, that has to be broken to give massive fermions out of massless one. So we start with a theory, if you wish, if we are going to do things for short-range interaction, which is as much as possible related to electromagnetism, we have to do something which is breaking the symmetry both from the particle which transmit the interaction and the constituents, which are fermions. Suppose you know what it is, if you don't, forget the word. And both they point towards spontaneous symmetry breaking, because that's why you have to explain mass. Because if you start with something that looks like electromagnetism, and we'll see it's very important that we do something like that, then you have to find a reason for them to get mass. And that's the basic point. So, what is spontaneous symmetry breaking? Let's suppose that this would be the solution. Yeah? We start with a theory where everything is massless, and then we break the symmetry, and somehow both the bosons, which are the particle which transmit the forces, and the fermions, which are the constituent of matter, ordinary constituent, are massless, and we want them to get mass. And so, because this was, as I said, a consequence of symmetry, can we break the symmetry? Spontaneous breaking of symmetry is the following thing. You see, you have here a table, which is, actually it's our table, but that is not important. That's a table which has been dressed in such a way that you put the glass in the middle of the adjacent plates. So this has a symmetry, obviously, because going around one way or the other way, you meet the same succession of objects. So this has a right-left symmetry. Now, the guests are coming, and they are thirsty, of course, and they want to take a glass. Now, they are perfectly ambidextrous for the experiment. They don't, so the only thing that we can do is choose one of them by pure random decision, or random fact, let's say. But if one takes, let's say, the right hand, the glass which is on his right hand side, with his right hand, then everybody has follow suit if you want the system to arrive at a thermodynamical equilibrium and not everyone killing each other. So that is what you have to do. This is spontaneous symmetry breaking. Now, does that exist in physics? Yes. The simplest example, it exists in many phase transition, like, for instance, the onset of a permanent magnet, of ferromagnetism. Ferromagnetic materials are materials which are composed of atomic little magnets, call them spin, because actually that's what they are, and such a way that neighboring ones have a tendency to be parallel to each other. Of course, the whole system doesn't have any particular orientation. It's completely isotropic in space. But at low temperature, where the disordering effect of temperature is not there, they will choose the lowest energy thing. And if two of them orient, like the glasses, everything else will follow suit. And so the thing will orient in one direction. Which direction? Any direction. course, there's nothing that prevents one or not. So the system will necessarily break the symmetry, and it's just as a consequence of their interaction, so that's spontaneous breaking of symmetry. Same effect, except that there are a lot of possibilities here, because it's all direction of space. You can see that a little bit more mathematically by drawing the potential, the thermodynamic potential, which is essentially the Gibbs potential per spin, for those who want to know exactly names. And in the plane of the potential and the magnetization along Z, you see that at high temperature, bigger than a temperature called Tc, then the system has only one minimum, and the system goes to the minimum of that potential. And so there's no magnetization in the VMZ plane, and because of the symmetry of rotation in space, that's also true in any transverse direction, so magnetization is zero at high temperature. But at low temperature, the system develops a double minimum which are connected to a valley indicated by the green arrow, and then the system will go to that minimum. Therefore, it will have to choose, like in the previous case, but now any point along that valley, that's a spontaneous breaking of symmetry. Right? Now, we can see two things here, that if you make a little fluctuation along along the condensation, or if you wish along the magnetization, fluctuate a little bit the magnetization, then you see that that costs energy. But if you make a little fluctuation around the green arrow in the space of momenta, then that will cost practically no energy. That means there are two types of modes that you can see here. There is a massive mode, which means massive, cost energy in the limit of long wavelength. That means the limit of constant motion. A massive mode, if we fluctuate in the direction of the potential, that is changing the magnetization, and the massless mode if we fluctuate in the direction of the valley. Right? Now this is in fact a general feature. The continuous symmetry is just a consequence of the broken symmetry, the fact that it's spontaneous broken symmetry, and that will build in the next transparency to a general theorem. While the massive boson, the constituent of the massive modes, quantum constituent, measure the rigidity of the broken phase, and these have mass in this non-relativistic approximation, but this can be shown and verified experimentally. Now there is one exception, which is superconductivity, and that will be as close as one could see to what I will explain to be the BEH mechanism when I will explain why it's necessary. Now, this thing is in space, in kind of the world of useful objects, right, that we use. But it exists also in the world of elementary particles. That has been shown by Nambu. It's a wonderful work, and not astonishingly, it's during the year 60, when that makes the transition to what I will explain later. So first thing, Nambu showed, I told you that in making a massive fermions out of a massless one, constituent, you break a phase symmetry, and that was the example Nambu did, and he showed that as a consequence, there is also, like in the spin, there is a zero mode particle, which actually is mathematically a pseudoscalar, and which he identified to the chiral limit of the pion. This was a breakthrough in the understanding of interactions. And there is a massive one which measures the rigidity of the transition. I will more than that, explain a more simple system, which is very similar to the magnetization, where we have a potential for a field, it's called a scalar field. I will explain later what that means. I suppose most of you know a little bit about that. So we have two fields, two real fields, phi 1, phi 2, or equivalently a complex one. And you see that the potential that we draw in the plane phi 1, phi 2 has exactly the same, looks the same as the ferromagnetic potential. And therefore, there can be a broken symmetry when the system chooses lowest potential by having the lowest energy possible, and the system orients all the scalar into the phi 1 direction. Right? So that means that we will have a massive scalar boson, which is the quantum, the bosons are the quantum excitation of a field that has a classical limit. And so massive scalar boson, which is the fluctuation of phi 1. And we have massless. Now, the massive scalar boson, one thing, is the average of the phi 1, which means that there is a lot of bosons in this to build up this picture. In other words, the bosons, this expression which is here, phi 1, means the condensate of scalar boson. And so we have massive scalar bosons which condense and give rise to individual ones which exist in the phi 1 and in the little phi. And we have, as previously, as in ferromagnetism, we have a massless Nambu-Goldstone boson, which is the one that goes along the valley, which therefore starts in the phi 2 direction, little motion in the phi 2 direction. So, this is a simple model, and it's important to understand it very simply. And I will spend 5 minutes to explain this more, such a way that you can draw away all the mathematics, which I didn't do very much, but anyway, that might, it's good to understand directly. So, in this picture, you have, on the first row, you have a representation of the condensate. All the fields are in the direction phi 1. In other words, all the bosons is phi 1 boson which condensates, right? And this makes a field. And now suppose I rotate all of this. We know that's a broken symmetry. It's like moving in the valley. That costs no energy. But I can do something else. I can move half of them a little bit and not the other. That is an excitation, costs energy, but not very much, because if I rotate them all, it costs nothing. So it's just a little bit of energy that costs here in the, where the different fields rub a little bit about each other when they have a different direction. And then you can do this. Doing this, the third row, is just constructing a wave. And that wave, therefore, when you go back to the top band, is going from very low, small wavelengths to large wavelengths. So you see that in the limit of large wavelengths, this describes excitation which goes to zero energy. Therefore, the constituents, which are bosons, the constituents which are little particles, these constituents have in that limit no energy, and that's only possible if they have no mass. Therefore, this is the theorem that tells you that there are Nambu-Goldstone bosons when you break the symmetry. And so these are massless modes whose constituents are the massless bosons, Nambu-Goldstone bosons, for reasons which are obvious. Now there is another mode that can happen, which is a massive mode. This is just as previously when you stretch around the thing that you move a little bit, you make fluctuation in the direction of the potential in the condensate, and these are massive scalar bosons. It's a massive mode, and its constituents are massive scalar bosons. If there are things you don't know, don't understand, maybe you can ask me, but then it may be later that you decide. Well, okay. If nobody says anything, you'll say later. We'll see. Yeah, because I see that I have the impression that not everybody understands. So I thought that you know, I'm not going to make a philosophy course here, but there are things that you have to realize that there are things that you can understand only fundamentally if you have the right background, and that takes time and effort. So for those, and I have the impression from the eyes I see that there are some of them which have not yet done that, therefore will never do the effort, I don't know, then they should satisfy with something like this, with something, not saying I haven't understood anything, and just say that after all, one should satisfy by saying that it's important to understand a little bit. There's something like a partial understanding that you cannot get more if you don't have the background, that you have to understand.
They will have a course of that.
But they don't have yet. Well, that's, okay, so fine, I can see that. And okay, so now I'm talking about Englert, Higgs mechanism. Now, it's the same thing as spontaneous symmetry breaking, except for one thing. You see, let's take the Goldstone model, the one I showed. You have the potential there, and then you have this condensate there, which is there, and so we have the symmetry, which is this U1 symmetry, rotation in the phi1, phi2 plane. Now, normally, this symmetry is a symmetry that's independent of the position in space. Namely, if you rotate this, I say it costs no energy. It costs no energy because rotate all the spin in space the same way. That's called a global symmetry. Now, let's suppose we invent something which is called the local symmetry, meaning that costs no energy to move them each, not spin, but spin is the equivalent in ferromagnetism, one of these fields, phi1, you can move any of them, rotate them, keeping the length, and you say this is also a symmetry. You want this to be a symmetry. That would be called the local symmetry. Now you can tell me that's nonsense, because how? I just explained that when I do this, it costs energy. Now I say, well, no, it costs no energy, because we are going to make a local symmetry. Nonsense, yes, except if you invent a new field, which is precisely the gauge field I talked in my first transparency, which is designed in such a way that each time it would cost energy, that compensates exactly the energy it would cost, so it costs no energy. In other words, what you have here is a local symmetry, we'll see, and for that you have to introduce a new field, which is a gauge field. In other words, now it costs no energy to rotate the spin individually. So now we would say, okay, we have, if we don't think too much, we say we have two types of bosons, the massive and the massless one as before. This is an obvious mistake, because I just said that this doesn't cost any energy, so that's why I make this effort to explain this. This cannot exist, because that would be a symmetry. In other words, the point is that we don't go from one vacuum to another vacuum like this. or to one vacuum to another vacuum by doing this. We just have different verification of the different formulation, redundant formulation of what the vacuum is, which is what happens, and you will learn it, for those who will learn physics enough, that this is what always happens when you have a potential. You can have honorary, the rotation in the valley is a gauge rotation, as one said. It's a thing which is not something measurable. So there can't be any Goldstone boson. It's trivial and obvious. This is not a very big mathematical proof, but it's 100% correct. And, but they were proved at that time, but for some reason, these proofs at that time did not use this simple unicity of the vacuum, which is redundant because of the local symmetry. And that was, in my opinion, only realized more than 10 years later by Elitzur. And so, now something again is wrong. You have no Goldstone boson because you have a local symmetry. But if you have a local symmetry, what's going on? Because previously you had two types of degrees of freedom, these one and those one. Now you have only one. That can't be. So things don't disappear like this. So the only possibility is to be absorbed in the gauge field. How can it be absorbed in the gauge field? Well, I said it's massless, right? The gauge field were massless. But massless field can do a thing that massive field cannot do. Namely, they can have only transverse polarization. Massive field cannot have that because massive field can always be brought to rest by some observer, and then it makes no sense to say that they have transverse to the direction of motion because there's no motion. So the massive object must have 3 dimensions, and actually, as you probably have already heard, the massless one have only 2. And these are not only necessary conditions, they are necessary insufficient conditions. Massless field, like the photon, has always transverse degrees of freedom. It always vibrates perpendicularly the electric field to the direction of motion. This is the well-known polarization of light. And, but massive one have necessarily 3. So the only way you have to absorb the gauge field, well, there are 2, so they must have 3. That's the only way they can do that. And to do that, well, if they have 3, then they have mass. So the fact that the Goldstone boson disappears implies that the field becomes massive and has now 3 degrees of freedom, and therefore we have built a mechanism to have short-range forces. Now this is, in my opinion, absolutely correct from beginning to end, except one thing, that physics is a quantitative theory, it's a quantitative field, and you have to be able to answer not only this, but you have also to compute the mass. So let me show a little bit how that works. You see, I start again with this, but now I look what happens to the gauge field. Now time runs here in these Feynman grams from left to right. And you see that the first and the second diagram which are there are interacting the gauge field mu with the condensate, because the phi with this bracket were the value of the condensate of scalar bosons. So they interact with this, and this gives rise to an object which is called the polarization of the vacuum, which has this property where Q is a 4 momentum, Q0 is the energy, Q spatial is the ordinary momentum, and the fact that this is multiplied by something which is a constant implies that this constant is a mass. You can do that very simply by summing all of these, and you get such an expression, and the field theoretic person immediately recognized that the 0 of the denominator is an equation for the mass of the particle, which in this case is e squared phi. So it's very easy to understand exactly, but I'm afraid if I start to explain everything, one won't take an hour, it will take more. And so let's assume you understand that, and if you don't, you can ask me at the end, I will explain. And so the zero of the denominator is the mass, and therefore q squared is equal to this, and q, so the mass now is not at q squared equal to 0, but at q squared equal to em phi, so the mass is em phi squared. Now this is a very simple model, but where you have only a U1 local symmetry, but you can generalize that to many symmetries and to all what's kind of Lie group symmetries, and this is just that expression, which has much more indices, but essentially it's the same, and we had that expression already in 64 in our paper. Now, what happens to the massive scalar, which, by the way, receives a knot of name now. As I said, it was already in the Goldstone paper, but it's called sometimes the Higgs, sometimes the BH, so I call it either phi 1 or the H boson. I don't have anything to do with the dominance of some language over the others. And here, this is again the upper, I explained the mechanism which give mass to generalized photon, that is to Yang-Mills field, but actually the same thing happens to the electrons and to the structure, to the constituent of matter, the fermions. Because, you see, you can look at this Feynman diagram by taking the time going the other way, perpendicularly to the diagram, and then phi is only the expectation value of phi, or the bracket phi, is just a part of the phi. What's left over is the scalar boson that you're supposed to detect in experiments. And so they're coupled in the same way, obviously, as this one. So if you replace one of these phi by the fluctuation of the phi, you get how the phi 1, or the H boson, the scalar boson, the massive one, interact with two massive objects, two gauge fields which acquire mass. And this is E squared times 1 of the phi, and phi times E is the mass of the vector boson, so it's EMV. And but we can have the same thing with fermions. We have a fermion that propagates, again going perpendicularly to it, we can compute the mass. And the fermion, the mass then is just lambda times phi. Lambda being the coupling constant. It's called the Yukawa coupling, it doesn't matter. M is just phi, which would replace the fluctuation by the condensate. So when the fermion interact with the condensate, that's a particular realization of Nambu's way of getting mass to the system, to the fermion, and we get lambda f, phi times lambda f is the mass, and therefore the H interact with lambda f, and which therefore is equal to mf times mv times E, because mv over E is phi. These are really trivial mathematics, but if you don't remember, don't follow, it doesn't matter. You can do that very easily. Now, so this is quantitatively. Now the important thing is, why did we do all of this, right? Because, as I say, in the beginning, we need to have a theory of mass because we had the idea that it has to come from a theory where the mass is strictly zero because of symmetry principle. Symmetry for the electrons, for the fermions, and symmetry for the forces. But you could say, well, why should I do that? Well, who cares about the symmetry? I could start with particles which have a given mass and so on. This is true, you could do that. but it doesn't work in quantum mechanics. So this is the most important point of the whole thing and the most difficult, I'm sorry, to understand. But I, again, will try to give a understanding which is proportional to the back knowledge you have. We had this propagator. This is called a propagator. The way the gauge field propagates, the numerator gives you the value of the mass, right? And so we have this, it gives the value of the mass. And the important point is that the numerator here has something which when Q, the momentum or the energy, becomes very large, Q squared is the energy squared minus the square of the momentum, Q squared in the denominator and Q mu Q nu in the numerator is something that generally is of order 1, even when the energy goes very high. And when the energy is very high, what happens to most of the theory you can write is that you cannot do that quantum mechanically because you get divergence that cannot be controlled. The technical term is the theory is not renormalizable. And so here we were nearly convinced at that time that the theory was renormalizable, and because the first idea was to do things like electrodynamics, and this type of form of thing is exactly what you can have in electrodynamics, except that there is no mass, but at high energy that doesn't play any role. So this is why we, the fact that it's my name and not both name is just accidental, this is something that we both had, Bart and myself, in, actually it's an amusing story, but we'll keep it for later. And is that we expected the theory to be renormalizable. That means to be consistent quantum mechanically. But there's a catch, because I said poles here, number of the denominator gives the mass, but we have one here, another one. So we have a zero mass particle in addition. Well, that can't be, that doesn't exist in nature. In addition, the sign is wrong. Signs are important in physics, and the fact that the sign is wrong means that this is a theory that violates unitarity. So it's not right. It doesn't violate, the sum of probabilities is not one, if you wish. So, what's happening? Well, here is an identity that you can check that this is an identity, and I'll explain the terms. The left term is what we did. But in a gauge theory, which has all these possibility of formulating things in different ways, there are different ways. And Higgs formulated his theory classically by making a change, I mean, he wrote equation of motion. He didn't do that, but he could have done it. So let's do it at his place. He changed the definition of the potential by making a change of variable, and if he would have done that quantum mechanically, he would have written that. And that is, again, something that looks valid. It doesn't have this disease of having the Q squared, so it is a consistent unitary theory. But at infinity, these terms get very high. And therefore, this theory doesn't look to be renormalizable. So we have a theory that is renormalizable, means that the divergence at high energy is sufficiently soft that you know how to handle it. And I will not give a course of renormalization here. So we have a theory which is renormalizable, and another approach which is unitary. This one doesn't seem to be unitary. This one doesn't seem to be renormalizable. But it's a gauge theory, so it should be both. And it's both, and the answer is in that term. And here, this is something so nice. Well, I like it so nice. Of course, those who are completely lost in the mathematics will not see the nicety in that, but maybe motivated to maybe do some mathematics. The point is that here, let's take this disintegration of the mu into the electron, and you see that you have here this W meson. It's one of the gauge bosons that require mass, that acquires mass by what we do. And we have used consistently this formulation. Where is this? Yeah. We have used this. Now, how this is an identity now? What is this term? Well, we forgot the first term, actually, of the Nambu-Goldstone boson. And this one couples here with a constant which comes out from this. Suppose you multiply both ends of this identity by the square of the coupling constant, which I call E. So you have E here, you have a squared of E. This is the divergence, Q mu. That means this is the mass, actually, of the particle. So here you have E m mu over mv, and here you have E over mv. So that means that just before, in the previous transparency, I showed you how the things that you put in the model, which is the U-Kava potential, comes out, actually. And this is this term here is the effect of the U-Kava potential. This is a bit tricky, but I wanted for those who have a little bit of knowledge to appreciate the subtlety involved in showing this is why this is renormalizable. It's because this term doesn't look renormalizable, but if you look at more detail, it is. And it is because of the transmutation of this into a coupling of the U-Kava potential with the electron, which is a renormalizable term. And so you have this, and therefore this theory works, and you see that this term here is cancelled by that term in the limit where Q goes to 0. Therefore, the Goldstone boson kills this unitarity violating term. They are not, and kills himself. They are not there anymore. According to the theorem I proved, this is an example how it's realized mathematically. It's a very subtle way, and at the same time, it destroys what would destroy unitarity and makes the theory correct. Well, this is a bit difficult. I don't know, maybe I should not have done this in front of this auditorium, but okay, I did it, so what can I do? I cannot go to the past, right? So, but this is a little bit of trickiness, but to realize how much more thinking has to done to be doing that not only at the first order, but to all orders. This is what has been done by Weltman and de Hoof, for which they got the Nobel Prize for that, and showing that the theory is consistent, which is quantum mechanically to all orders in perturbation theory. And therefore, that is why the theory is interesting. If that would not be true, you could take that theory and put it in the wastebasket, because it would not be interesting from the point of view of getting things in which you can prove it by experiment, because now you can make detailed provision on experiment, and you can verify it, and it has been verified. And this brings me to the the main application of this theory was the construction of what's called the standard model, which contains all the known particles and all the laws which verifies them. They are, well, I have to do this again. Okay, now it's here. This is the theory which was done in 67. It was started in 67 because the shaded part, you see now we know there are 4 types of interactions. That's the one we know today, and we know the laws and everything. They're all gauge theories, everything. And the weak interaction, those which are responsible for radioactive decay. These are a direct application of our mechanism, and they lead to these particle 2 W's and a Z. And this is the range. This range means that it's long range, it's infinite, that's right. And there are a photon and a graviton still to be discovered. And the shaded part of this is what was known at that time. The rest was known on the rest of the 20th century. It was predicted earlier, but not things. Well, the strong interaction were interested, but this is what I want to show in the next. These transparencies, these things are the particles which are connected to the force, and the particle connected to the to the particle are here, and the first line is the particle connected to the one to form the proton and the neutron, 2 quarks. There are 3 U quarks, 3 down quarks, and then we have the mu. And again, these were what's known in 64, and the others were known later. And finally, the whole thing becomes a consistent theory with mass because of the mechanism, which was verified by the discovery of its constituent, which is the scalar boson, or the BH boson. So let me say a few words on the discovery. The discovery was done at CERN. I'm not going to give an experimental discourse, and I think you said tired. I think I have 5 minutes left here, so that's a little bit too not enough, but okay. So this here is the schematically you see the tunnel in which you have opposite beams of protons which are circling into it and colliding at some points. And this tunnel is, as you probably know, 27 kilometers length, and the proton run there quite close to the velocity of light, because they can do, let's say, something like, I would say, 37, so something like 10,000 times the circle before they collide, for instance. In 1 second, let's say, they can collide before. And this is what, and inside you have the beams are circling inside these supercooled magnets, which orient them at the region where the tunnel turns and correct the V. And then they arrive to the big things that here people here work in the Atlas, so they will recognize. This is the Atlas detector where you have the collision. How many collisions? Well, at that time, the collisions were close to 1 billion collisions per second, and which means that it's a lot of things to handle and to analyze, but apparently this is a remarkable success in technology that has been done. And this is the other Atlas. This is at the opposite of the diameter. This is in France, the other is in Switzerland. And I want just to show a simple example of one of the results. You will see in the right-hand side there, up here, you will see the moment where the system has been analyzed. And here, as a function of the mass, you compute from the standard model, you can compute from the standard model how much of the effect that you're finally measuring, which is a disintegration of the scalar boson into, let's say, 4 leptons, let's say it's 4 muons. And, but that can occur either with the scalar or with all the other interaction that's called the background. Now, so you measure everything, and you can compare the result with the result for any value here of the mass, which is here. You can compute the value of you can compare the value you find with the prediction of the standard model. Now, what happens is this. As a course of time, you see in blue, that is what you would expect from the standard model, and the whole measurement works everywhere except for this tiny and very sharp red peak. But we have the computation that to the comparison with the experiment is done for the thing that would be if there was no scalar boson. So this seems to be the scalar boson, and it is, because they check this and over, and it has all the properties. So you check not only the scalar model, not only the scalar boson, but also the standard model, and you check it in different type of channel averaging. And the remarkable thing is that the thing happens at this level, energy level, as being something which is like an elementary particle, and it's a scalar. It's the first time a scalar, which is a particle with no spin, which means, as far as the orientation, that it has no orientation, as it should, because it condenses in space, and space has no orientation. So it must be a spin zero, and it is, and all of that has been checked. Of course, the point which I did mention, they found the value of the mass, which is something of the order of 25 times the proton mass, 25 GeV, and well, there are many things I want to say, but I will not say them. They decay so fast, of course, that you cannot see them. And you cannot see even the decay into 2Zs, which is here, because Zs lived not long enough, and then you see only the traces of the final disintegration part. So, where are we now? A few words on the unknown. This, of course, will be very condensed because the unknown is very large, and I have -5 minutes to discuss it, so I will just go very fast. But I want to say a few things. The neutrinos in the theory discuss a particle with no mass, which is reasonable, except that they have one. And that has been discovered late, but they are very small. Where do they come from? For the moment, it's unclear, but it's proven because the mass, to some extent, has been measured. Now, people have invented, if the scalar boson would be a real elementary particle, like the electrons, like the quarks, like all of this, then you would think that, then many people argue, but there are leaks in the argument. I tell you that this implies a new symmetry, which is called supersymmetry, in which you would have a doubling of all the particles you have. Now, none of this had been seen. So if they exist, they are higher energy. One of the reasons people do now want to get the LHC working at higher energy is because they want to discover supersymmetry. Maybe they will, and maybe not. You have to know. It's not so sure, and the arguments for supersymmetry are not tight. Finally, I've done all of this. I say it's wonderful, we have all the particles we know. Yes, for one exception, that there is particles, or maybe it's not particles, but something that interact with gravity that we don't see. This is called dark matter. And dark matter is 6 times more important in mass than the mass we have. One says, generally, you'll see, and there's something in this sentence that you will not understand. Now, that, but in 2 minutes, yes, -2 minutes or +2 minutes, I don't know, that the energy, the mass that we see counts correctly for something like 4%, 4 to 5% of the mass of the universe. And which is there, count about for 26%, let's say. that all over made 30%, so what was the rest? One moment. So there's a lot of things we don't see. We know it's there because we know in the way the cluster of galaxies and things like that behave, that we know there is matter there, because everything interacts with gravity, but with the rest, we have not found it. So this is something which is one of the most interesting and intriguing and challenging unknown. What is dark matter, and will we find it? The cosmological implication of what we have done is really due to the fact that, you see, it's very similar. That this is the ferromagnetic drawing I got for the ferromagnetism, and remember, for the from the Goldstone model, or for the simplest BEH model, which is essentially the same, it becomes local symmetry. One has a system has a major of 125. So we expect something very similar than here, that at high temperature there's a phase transition to something where there's no ferromagnetism. Here, it just means that this condensate or scalar boson just evaporates. If it evaporates, where I showed you that the mass comes from the condensate, it means essentially all masses go essentially, at least in perturbation theory, goes to zero. And there are only long-range forces. So the universe at that temperature, which would be something like 10 to the 15, 10 to the 16 degree centigrade, let's say, that is something like a million of a billion of a degree, then the world is completely suddenly different, and the world is with only long-range forces and masses particle, except if something else happens, of course. And so this means, how is this possible? Well, because, you see, the universe in the beginning was very hot, and it cooled down due to the expansion of the universe. And that we know in detail. So this phase transition, which is at that temperature of 10 to the 15 or 10 to the 16, which means a million of a billion, occur about 100 of a billionth of a second after the beginning of the universe, which we know had a beginning. And so that now asks, well, we have neglected the quantization of gravity, but here is the point now that we need it, because we are approaching very close now to the origin of the universe. This is not that close, but as you will see, we can go much closer with that. This is 10 to minus 11, a million of a billion of a second is a very long time for cosmologists. Very long, very long. Many things can happen in that time. And things probably that are the most important one for us. But so we need, if we want to go to really the beginning, we need to understand something that we could pass by for the moment, which is the quantization of gravity. And one indication is the 70% of the matter we don't know. Why is that an indication? It's an indication because this is not ordinary matter. This is matter that keeps its density while the expansion increases. This is what was called also, it looks like it at least, a cosmological constant. Having a cosmological constant classically, you can always do that. And Einstein did it a century ago, essentially, a little bit more. But we know that it's not consistent with what we know in quantum mechanics. And I am pretty sure, it's a commitment, that this is possible only if you go to quantum gravity to understand that problem. Yeah. And so I said it delineates the known from the unknown in the in the small world, but also in the large world, because you see this line is where it delineates. You have here on the right all things coming from the formation of the proton, 10 minus 4 seconds, and then up to the creation of low, and finally the creation of the atoms, which are there where you can measure it directly, because then the photons go, the universe is transparent, and you can see the photons up to no. They just get larger wavelength, and I'm finishing the thing now. And so this is what you measure when you look things at that moment where the atoms are formed. And you look and you find, and these are the fluctuation, very tiny fluctuation of the temperature in the radiation, which comes from all the direction, which is the remnant of something that happens in the Big Bang. But you see it late. You see it late because you have to first wait that atoms are formed and that they, so the light can go through because the atom is neutral. So it goes through, and then you see, and there are little fluctuations which were discovered only now because these are very small ones, fluctuation 10 to the minus 5, the values. And, but there are theories claiming that in the beginning things were exponentially fast. And if that is true, and there are many reasons to be true, then we can explore the origin of this type of things up to moments which are very close to the origin. And what is very important is that the structure which you see there can be interpreted as the result of quantum fluctuation, means vibration of essentially what's called a vacuum. And that can be done, and then there is the question that maybe the whole birth of the universe is itself a quantum fluctuation. This actually is not new. The first one to suggest that was Lemaitre in the 30s. And then Tryon does it, and then we, that is brought myself and Günzig, not only try to explain that, to explain it from a quantum fluctuation, but derive from this quantum fluctuation an exponential expansion in the beginning. That is what was later called inflation. So actually the last thing was actually done before all the rest. Well, it's not yet completely accepted, but it will be. Thank you.
So thank you very much for this excellent talk. I don't know if you understood the last part, that the claim is that they have discovered also what is called now inflation. And there are some other people, Guth and Linde, who claim a Nobel Prize, but probably Professor Englert deserves another one. Okay, I think I was back there, so I could not see. I lost half of your talk, but I think
you're not the only one.
Okay. But as far I could say about the unitarity argument, I think you should know that Professor Tichtopoulos, who was with Cornwall, who pointed out the unitarity argument in the first place.
Oh.
Yeah. Is that true? Okay, so we will take a few questions only because there is a pressure of time. We would like...
No, I didn't want to say that we did, we realized the unitary gap. We just, at that moment, we realized it should be renormalizable.
Sure.
That's why I said that things were more subtle than they looked. Right?
Yeah, that's clear.
We didn't have the answer to all the subtlety of it. Actually, I want to say that the interpretation of the renormalization by the simple case, I think, is Jean-Marie Frère.
Yes. Okay, so we take very few questions because we would like to take Professor Englert to Sunion today, and closes rather early. So, who wants to ask some questions? Yeah, so who of the junior ones, the students, would like to ask a question?
Hello, yeah. We talk about massive and massless field. About massive and massless field. Yes. When we talk about the Higgs field, the Higgsian field, if I'm allowed to call it so.
The Higgs field, I don't know what it is. And you mean that's the field?
This is how I read it in literature.
Well, what you call the Higgs field is the field which I call phi1, right?
Yeah, but and this field, it's massive or massless? I mean, it comes from the boson, actually. Because when we talk about...
anything that comes out of it, from the boson interaction. Then,
well, one point maybe, if I interrupt you first, is that you can check the literature. And the paper of Brown and Englert was clearly before, and they did everything. Right? Of course, maybe they didn't know each other, but they didn't call it the Higgs fields because he was
violating causality. Because
anyway, but the rest.
Okay. No, but I think independently of the name question, I think what you ask is essentially the mass of the field. Now you have to be careful. I showed clearly that the field has two components, if you wish, like you wish if you have, it's a very bad analogy, but nevertheless, if you have water in and molecule of the vapor, you have the condensate and you have the vapor. Now, what you measure here, the condensate is the field that essentially for 99.999% is the object that gives mass to the particle. That is the condensate. That by definition pervades everything, the universe and wherever. Taking this to have a mass is nonsense. The concept of mass does not apply to such an object. It does apply to the fluctuation of this object, and the fluctuation of this object is what you measure, or at least its constituent. That is what you measure at CERN.
The wavelength, actually.
The waves is, no, it's all waves. Except that one part of the wave, this is the whole mechanism, the one part of the wave condense into something which has all over the place zero momentum, zero work, the absence of gravity, of course, and pervades everything. That's the condensate. That is something that fills everything, and so it doesn't move, it doesn't act, so you can't tell about this. The notion of mass does not apply to that object. It applies to the fluctuation of this object, which you can Fourier transform as waves, and these waves have quantum mechanically constituents, which are particles, which are bosons, and these are the things that you measure individually.
Thanks a lot for the opportunity anyway, too.
Thank you very much. Okay, some more questions? Do I see more? Maybe some senior colleague who, yeah, please.
Well, superconductivity has the same type of object. It's a little bit, of course, the reason why many people, well, at the end, I think Anderson understood, but most of the people, including ourselves actually, did not take our intuition from that. The reason was that it's in the original paper of Anderson, it was, well, essentially it is, up to the end, a non-relativistic theory. And in the non-relativistic theory, the mass, or what plays the role of the mass of the longitudinal part, is a different mass than the mass that corresponds to the whole thing. It's the relativity, it's a non-relativistic theory. And essentially, the mass of the particle was the plasma of the longitudinal part. It's called the plasma oscillation, right? Which is the thing. And the plasma oscillation, the reason why people did not, I think, the reason why people were not immediately understood the relation with this mechanism, in a sense it is the same, but is that the plasma oscillation exists in ordinary metals as well in this metal. So it was not something which was specific to superconductivity. Normal matter have also oscillation, practically at the same frequency. So, so the thing was a little bit difficult to untangle at that moment, and because it appeared, if you wish directly, and it was right actually, as an effect of the electron correlation of the effect, the long-range, the Coulomb interactions essentially, and the screening of the Coulomb interaction. This is what gives rise to the plasma oscillation in general, and still there too is also the same thing. And, but what happens is that it swallowed the longitudinal interaction in the plasma oscillation, and that was truly the same mechanism as here. But it was not clear to many people, including ourselves, that the phenomena is, well, once you have it, it's clear that it comes from there, in a sense, that this is a ancestor.
But you were inspired by Nabu, as
much more by Nabu, yes. And now for Higgs, I don't know. No, I think he was also, well, he was inspired also by Nabu. Well, Nabu made an analysis, actually, of Anderson in field theoretic language. And that was much clearer at that time, for me at least.
Fine. I don't see, yeah, okay. Yeah.
Is that true that with the Higgs field we can unify all the other fields to one?
I repeat that I don't know what the Higgs field is. And, what do you mean? You mean, no,
you mean this
independently of the game of the name, independently of that, do you mean the expectation value, or do you mean the full field, including the fluctuation?
Generally, with the discovery of the Higgs...
Yeah. I know him. It's okay.
So what is the question exactly?
What is the question? No, quite.
Yeah. Let's hear the question.
Years ago, when the Higgs was discovered, they said that we are one step closer to unify all the fields, the electromagnetic, the gravity, and all the other fields to one due to the Higgs field. Is that true, or they are just...
Well, no, you were closer, of course, to unify, it has been done, the electromagnetic field with a weak interaction. Whether they are, the strong interaction is a different issue. It can be related by duality to something like that, but it's a completely different issue, in a sense. You have to go to magnetic one. And, but for the rest, it might be that theory which was called as grand unified theory, which unifies all the known interaction that we are for the moment, that we know for the moment, and which is something which is for the moment conjectural. That would be something that could be done by the same mechanism, not probably by the same field, but by something, by another one.
So it has nothing to do with the Higgs field?
Or you mean the one for the grand unified theory? Not that I think. I don't think so.
No, well, the grand unified theory is a generalization of the electroweak model, so it has similar features, of course.
It has similar feature. Whether you can relate it by some renormalization picture, it looks at first sight very hard.
Okay, and this will be the last question, I think.
I'd like to ask, in the end, after proposing a theory about the mechanism by which all particles gain their mass,
The elementary one, the constituent. Don't say that the mass of everything comes from that, right? That's not true. Yes.
does the boson you proposed itself have this fundamental property called its mass that through the mechanism it sends it to some of the other constituent particles, or is there something else about the boson you proposed that gives itself its mass?
No, that's a very good question. I mean, it has nothing to do with the mass of the field. It has to do with the fact that having scalar particles have the property that they can, if you invent or discover, that question of semantics for the moment, if you have the right potential, which is the one I draw, then you can form a condensate. And such a condensate could only be done by a scalar, not even by a pseudoscalar, because you want to have it as something that exists on large scale. In other words, pervade up to the universe. So we know that the universe doesn't have any preferred direction. So that, and no preferred orientation, that excludes any other type of particle than a scalar one, right? So it is the fact that it's the scalar field that gives rise to a condensate. Now, to go further into your question, so the mass of this, which has to do with the rigidity of the thing, and which is measured when you measure the fluctuation, that has nothing to do with the fact that it gives mass to the other thing. That is not. Actually, it's not even clear that you need the scalar boson as an elementary object. You see, many people have constructed theory in which what you need is a condensate. You need a condensate which has no orientation, plays the role of what you could get by scalar field, but doesn't have to be a scalar field. It could be something else. Now, the most amazing thing, there have been a lot of theories called by a nice name, like Technicolor, which unfortunately exists and is worth only if there is an extended Technicolor. And for those who have done this theory, it's very nice, but it becomes such a mess that well, personally, I'm happy that this is not the case, although in the beginning, when we proposed the theory, we proposed the two alternatives. So it is the fact that you have a condensate which can exist either by a scalar, or the scalar is an approximate, or even not an approximate description of this, and provided you make a condensate, you can give mass to the gauge bosons and to the fermions. You can do that once you have a condensate.
So are you sure you want a question? Okay, maybe a short question and we finish.
A short question means a short answer. Okay, I'll try.
If we accept that vacuum energy gravitates,
Excuse me?
if we accept that vacuum energy gravitates, then your mechanism, the Englert-Higgs mechanism, predicts a cosmological constant, except if you apply a very precise fine-tuning. So at the time you constructed your theory,
Yes.
were you concerned, did you bother about the cosmological?
Yeah, I know some people have been concerned by that.
But you, at that time,
I've never been concerned by that, and I tell you why. I tell you why. Because I think the people who were concerned, and there are some great names, which also I will not name them, which were concerned by that problem. I think it's a fictitious problem. Not that it's not that it's a stupid question, but the problem is that not only this condensate would give rise, if you take it without any fine-tuning, would give rise to an incredible cosmological constant which will close the universe very shortly. But just take the electrons. The electrons don't have a condensate, but they have vacuum fluctuation. Okay, when you compute them, there are many ways to compute them. You don't know exactly how, but the most natural thing just from dimensional analysis is that it should go like the 4th power of the mass. And when you compute this, and you would say, well, what is the cosmological effect of the electron which has these fluctuations, you find out that it would close the universe within the solar system. So this problem, in my opinion, is not different. And so we don't know. We have to, it's not different from this one. It's not because it's a scalar condensate or the fluctuation of an electron. They both give rise to cosmological constants which are complete nonsensical. And I think this is the reason, so my answer is not that short, but this is the reason why I say the problem of dark energy is a problem which can only be solved in quantum gravity. And I always was sure about that from the beginning. And we didn't know from that this was, so we didn't care about that problem because we didn't know how to solve it, but we didn't think it was a particular problem to this mechanism. That's
So I think we should thank Professor Englert. So, still,
I have to thank those who survived my lecture here, right?
So, the discussion can continue. I see more hands. So you can ask, Professor Englert will be the whole week around. Tomorrow we have this ceremony. So please come and discuss further. Thank you.